Hello and welcome back. In this video we're going to look at computing the area under a parametric curve. So to find the net area under the curve with parametric equations x equals f of t and y equals g of t, we can go back to how we found net area before. We took the integral of y dx, of our function of y as a function of x, and then times dx. But now that we have a set of parametric equations to represent x and y, well, we can replace the y with g of t, and then the dx here, if we use x equals f of t, the dx would be the derivative of f of t dt. Right? If we differentiate both sides of this parametric equation with respect to t, then we'll get dx dt equals f prime of t. If we move the dt over, we'll get dx equals f prime of t dt. So we can replace the dx with f prime of t dt. Now this is going to be an integral in terms of t, so our limits of integration will be in terms of t. Here we'll let t go from a to b, which remember that each value of t represents a point, so that's going to correspond with an x-coordinate, also a y-coordinate. But that's the integral that you're going to use to find the net area underneath a parametric curve. Now we say net area because when the curve is below the x-axis, in other words, when the curve has negative y values, then the areas are going to be signed negative, just like you would expect for the regular net area integral. And as you go from t equals a to t equals b, you've got to traverse the curve exactly once. This is something we never had to worry about when we had Cartesian functions and we were doing integrals, with x's and y's. We never had to worry about that because the graph never changed directions. Dx, when you consider a change in the x value, it was always moving in one direction, always moving in one direction. So, but as t goes from a to b, the curve could move to the right, it could move to the left, it could do all kinds of different things. And so we just have to be a little bit careful if we want this to really be computing the net area underneath the curve. We've got to make sure that on our interval of t, the curve is traversed exactly once. Otherwise, you might double count your area or triple count your area under the curve. So example 3 says, find the area under one arch of the following curve. It's x equals 2 times quantity t minus sine t, and then y equals 2 times quantity 1 minus cosine t. This kind of parametric equation set is called a cycloid. When you look at it, it looks like figure 2. It's kind of looks like it's something that's bouncing, but what it would model is like if you've ever ridden a bike and you've gotten a thorn stuck in your tire, or maybe like a nail or something, or maybe a piece of gravel, then this would model the motion of that thing that's stuck in your tire as you're riding your bike along, right? So if the nail was right here at the origin and you're rolling your tire over it, then when the nail gets stuck into your tire, it gets lifted up by the tire and moved over, and then eventually is going to go full circle around the tire and come back down and hit the ground. And every time it hits the ground, it makes that thumping noise, and you go, oh no, I have a flat tire. So that's what that's modeling right there. It's like something on the end of a circle that's rolling along the x-axis. Now it says, find the area under one arch of the following curve. Well, we have a general sense of what the graph looks like of the curve, but we don't know exactly where the arches start and end. Like what t value is going to be the start of this arch and what t value will be the end of this arch. So let's figure out what that is. We're going to note well, the start and end of the arch are going to correspond with places where the y value, the value of y, is equal to 0, right? That's what's in common between those points. It's the y-coordinate is equal to 0. So we can figure out where the y-coordinate is going to be 0 by setting 2 times quantity 1 minus cosine t equal to 0 and figuring out the values of t that make that happen. Oops. So y equals 0 when 2 times quantity 1 minus cosine t equals 0. Well, this happens when cosine t is equal to 1, which would happen when the x value on the unit circle is over to the right. So that would happen at t equals 0, at t equals pi over 2, and so on. Now, those are the t values. Those are not the x values. So at those t values, we can plug those t values into the x coordinate to figure out what the x coordinates are going to be for each of these arches, the ends of each of these arches. So at these t values, x equals, well, when t equals 0, you've got 0 minus 0, 0 minus sine 0, which is 0, times 2 is still 0. Then when t equals 2 pi, well, you're going to get 2 pi minus sine 2 pi. Sine 2 pi will be 0, so you just get 2 pi times 2, which is 4 pi. Notice actually that for each of these t values, 0, 2 pi, 4 pi, and so on, sine will be 0. And then you'll just be taking 2 times whatever that t value was. So essentially you're doubling the t values to get the x coordinates. So over on the coordinate system, we can mark this as x equals 0 for the start of the first arch, and then x equals 4 pi for the next arch, the end of that first arch. But that's just for looking at our picture and knowing what that looks like. Since we're going to be setting up our integral in terms of t, though, we'll want to note that that's t equals 0 to t equals 2 pi. So we're really mostly interested in the t values. After all, the x values were just for fun. Okay, so to find the area under that curve, under one arch, we're going to take the integral from t equals 0 to t equals 2 pi. I'm writing the t's there just for emphasis. And actually, let's go back up to where we have x equals 2 times quantity t minus sine t. We're going to write that that's like our f of t. And then y is equal to g of t. So g of t is the 2 times quantity 1 minus cosine t. That way we can identify, the f of t and the g of t in our definition, or the way that we wrote up the net area here. So we're going to have y, which is g of t, times dx, which is going to be f prime of t dt. In your mind, you can be thinking the integral of y dx if you want to. So that'll be 2, whoops. So that'll be 2 times 1 minus cosine t, and then times the derivative of f with respect to t. So that'll be 2 times 1 minus cosine t dt. It's kind of weird. They turned out to be the same, just by coincidence. Oops, so here's g of t first. Y is equal to g of t. And then the rest of it is f prime of t, and then dt. Now we can try to evaluate this integral, and I'll just take a couple of first steps. So we can multiply the 2's and bring that out. We have t goes from 0 to 2 pi. Distribute out the 1 minus cosine t. So we have 1 minus 2 cosine t plus cosine squared t dt. And then remember, if you have a cosine squared, you can lower the power of that into 1 plus cosine 2t all over 2, or in other words, 1/2 plus cosine t over half. So then from there you can work out how to integrate it, and you'll get 12 pi. just integrate term by term. You can actually combine the 1 and the half beforehand, so you get 3 halves. Gives you less things to have to plug into. So the area under one arch of the cycloid is, that particular cycloid, is 12 pi. That's the area under one arch. There we go. Now one final note before we leave net area. If x is decreasing as t increases, then this is going to sign the negative area. So in other words, if you have your parametric curve, and as t goes from, let's say t is going from 0 to pi, if the curve is moving to the left, so moving to the left, then your area is going to be signed negative, assuming that all these y values are positive. The area under that curve is going to be signed negative. And the reason for that is if x is decreasing as t increases, then your f prime of t, which is basically the derivative of x with respect to t, the f prime of t will be signed negative, and that's going to make the whole integral turn to negative. So again, if x is decreasing, if x is moving to the left as t is increasing, then that's going to flip the sign of your area. So that might have an unexpected consequence there if you're not looking out for it. So if you want to make sure that your area is positive, then you'll always want to make sure that x is increasing as t is increasing. Here's a quick example. Consider the parametric equations x equals cosine t and y equals 1. Just for practice, let's draw a sketch of that. Notice that y is always equal to 1, no matter what t is. So we know that our graph is going to be along a horizontal line, y equals 1. And then the x values are equal to cosine t. So as t is going, from negative infinity to infinity, the x values are just oscillating back and forth between 1 and negative 1. So the graph of that set of parametric equations is just going to be a horizontal line segment between x is negative 1 and x is 1, right there at y equals 1. And it's going to be oscillating back and forth as t is increasing. So we can't really give an exact direction of motion because it keeps going back and forth and back and forth and back and forth. Now it says if we set up the integral like t goes from 0 to pi, if we want to find, let's say we want to find the area under this curve, well, we know that area to be 2, right? If we set up our integral as t goes from 0 to pi, then we have y times the derivative of x with respect to t, dt. So y is 1, derivative of x with respect to t is negative sine t, and then we have our dt. You're going to get a negative area. If you finish that off, you have the integral of negative sine t is cosine t. If you plug in the limits of integration, you'll get cosine pi minus cosine 0, so that's negative 1 minus 1, which equals negative 2. Notice that the area here is signed negative. And the reason is that because as t goes from 0 to pi, x is going from 1 to negative 1. In other words, it's decreasing. This over here is where t is equal to 0. T is equal to 0. When t is equal to 0, you have x equals cosine 0, which is 1. So t equals 0 corresponds with that point 1, comma 1. Then t equals pi corresponds with point negative 1, comma 1. So in this version of the integral, you're actually moving to the left as t is increasing. So that's what caused that negative area under the curve to happen. It flipped the area under the curve to be negative. So instead, what we want to do is set up the integral like this. T goes from pi to 0, and then the rest of it's the same. So you'll have the 1 times negative sine t dt. If you work out that integral, the only thing that changes is the limits of integration, so you know that that'll flip the sign from this negative to a positive 2. So if you want your area to be positive, make sure that as t increases, that x is also increasing along your curve. Then you'll get a positive area under the curve. Thanks for watching this video, and see you in the next one.